Hi everyone. So this is a new video in the Mathematics Essentials series. The last one was on absolute value, so I wanted to cover some properties of absolute value. Properties of absolute value. Okay, and I'll cover three properties. I'll prove two of them, and I won't prove the third one because I'll end up proving that property in my series on mathematical analysis. Okay, so let's start with first property. So for every real number x, turns out that the absolute value of x squared is just equal to x squared. And the proof for this is going to be so simple that it kind of doesn't feel like we are doing anything at all, and we are just following the definition of absolute value. Yeah, the proof is really straightforward. So I'll just write the definition of absolute value here again, so we can look at it whilst we're doing our proofs. So for any real number x, the absolute value of x is given by this piecewise definition here. So it's just going to be x itself if x is greater than or equal to 0, and it's going to be negative x if x is less than 0. Okay, and remember that we want to stick to graphical and geometric intuitions about absolute value because it makes things easier to understand. So after I give the proofs, I'll kind of talk through a more graphical interpretation to get an intuition as to why the proof is true, even though we would have pretty strong algebraic intuitions about why these properties would be true. I mean, for example, if we look at this property, well, intuitively, squaring something always makes it positive. Okay, if we had a positive number and we squared it, which is just times in it by itself, it was already positive, and a positive times a positive is just going to give you something positive. And if it's negative, well, you're going to be timesing a negative by itself, and that would give us a positive in the end. So we're always going to get a positive out of squaring something. And here, notice that what's being said on the left-hand side, well, that's saying take the absolute value of x, which is just going to make it positive, and then square it. Okay? So, pretty straightforward algebraic intuitions as to why these are true. Probably won't go into a geometric handle for this, a way to think geometrically about this property. But let's go ahead and prove it. Okay, so this one's going to break down into cases. So first we'll suppose that x is greater than or equal to 0, because we need to account for the cases in which x is positive, negative, or 0, because it's a real number. So we'll work from the left-hand side and just end up with the right-hand side in this proof. So supposing that x is greater than or equal to 0, well, what would our definition of absolute value tell us then? It would tell us that it's just going to equal x. So let's take the absolute value of x and then square it. Okay, well, first we would resolve the absolute value bars before we square the absolute value of x. Well, since x is greater than or equal to 0, that's just going to be this case here, where we're told to just drop the absolute value bars and treat the absolute value of x as just x, okay, because absolute value just makes something positive, and we already have something positive. So drop the absolute value bars because we know it's positive and that the absolute value bars aren't really doing anything for us. But after we drop that, we are still left with this square. And that's the proof for the case of the case where x is greater than or equal to 0. Okay, so now we have to worry about this case. Well, suppose, go back to blue, write it over here. Suppose that x is strictly less than 0. Well, then what would happen? We'd have the absolute value of x squared, but our definition, if we focus on the absolute value bars first and ignore the square for a second, our definition tells us that if x is negative, in other words, less than 0, then the absolute value of x would just equal negative x. So this is going to equal negative x, but now we remember that this was squared. So we'll put it in brackets because we know that whatever comes out of the absolute value of x is going to end up being squared. Okay, but this has the effect of just timesing negative x by negative x, and you can see that these negatives would cancel and you'd just be left with x times itself, which is the same thing as x squared. And you see the left-hand side, we end up saying is equal to this over here, which was the original claim. Okay, so whichever case we have, the absolute value of x squared is going to just be x squared. And notice that the first case we did takes care of the case when x is actually equal to 0. Okay, 0 is neither negative nor positive, but we fit it into this case. We could have fitted it into this case, but convention is to take greater than or equal to 0 and strictly less than 0 in the algebraic definition of absolute value. So that's straightforward enough. Let's move on to another property. We'll write a little square here, which is what we typically write nowadays instead of QED. I forget what the Q is, but it's something. I forget what the E is actually too. Something demonstratus, but it's Latin for, you know, that which was to be shown. Anyways, the second property of absolute value that I want to do in this video is that for every pair of real numbers, okay, let's give them names, x and y. Well, we took the absolute value of x times y, so multiply x and y and then take their absolute value, turns out that you would just get the same thing as if you took the absolute value of x and the absolute value of y on their own and then multiplied the results together. Okay, so let's prove this. And there's going to be, well, kind of 4 cases, but really we only have to worry about 3. So the first case would be, x and y are both greater than or equal to 0. The second case would be both of them are strictly less than 0. Okay, the third case would be x is greater than or equal to 0 and y is less than 0. And the fourth case would just be the other way around, would be the third case the other way around. So y is greater than or equal to 0 and x is strictly less than 0. But really, case 3 and 4 are the same. They're really just saying that one of them is greater than or equal to 0 and the other is strictly less than 0. So even though there's 4 cases, we really only have to consider 3 because 3 and 4 are pretty much the same thing. It doesn't matter which one we say is greater than or equal to 0 and which one we say is less than 0. The same thing is going to happen. Okay, so case 1 is both of them are greater than or equal to 0. So x is greater than or equal to 0, and y is greater than or equal to 0. Well, what can we say about the absolute value of x times y? Well, notice that in our definition of absolute value, okay, it says that if x is greater than or equal to 0, you just treat it as x. But notice that if we had written this definition with y instead of x, it would be telling us to just treat y as y, okay? So, we could have just as well talked about y, some other variable. We didn't have to use the variable x in our definition of absolute value. So any real number y would just be y, so long as it's greater than or equal to 0, and negative y, so long as it's strictly less than 0, okay? So really what we're doing is we are applying both, we are applying this case to both x and y. So this would be the same thing. Tried to change to blue. As just x times y, okay? All right, if it's a bit unclear why we can just drop the absolute value bars and say that, let's just imagine we said first that, let x, y equal z, okay? Then we'd just be saying, well, the absolute value of z equals, or what does it equal? Then be looking at the definition. And this would be the case where since both x and y are equal to 0, well, positive time greater than or equal to 0, well, positive times a positive is going to be greater than or equal to 0. So this would be equivalent to saying z is greater than or equal to 0, and then we'd look at our definition of absolute value, and that would just tell us to drop the absolute value bars and treat the absolute value of z as just z, because we know z is greater than or equal to 0. Okay? So that's case 1. Case 2. Would just be that both of them are negative. So let's say x is strictly less than 0 and y is strictly less than 0. Well, actually, I should prove case 1 from both sides. Yeah, that's I haven't finished the proof from case 1. So getting back to case 1, if we note from here, okay, because I have to show that it equals this right-hand side. Once we say this part down here, then we know that because x is greater than or equal to 0 and y is greater than or equal to 0, x, I'll write this over here, x equals this, okay? And y equals this over here. So we can make that substitution and just say, well, since x equals the absolute value of x, because x is greater than or equal to 0, and similarly for y, x times y just equals the absolute value of x times the absolute value of y. So that's case 1 actually done. Moving on to case 2. So this is when x is less than 0 and y is less than 0. Notice that in this case, the absolute value of x times y, well, forgetting about the absolute value bars for a second, just x times y is going to be something positive. Okay, because you're going to have a negative times a negative inside those absolute value bars. So you're going to get something positive anyways. after you multiply those two negatives, x and y. So all absolute value does is make something positive. We know that it would be positive even if the absolute value bars weren't there. So we can say that that equals that. So the absolute value of x times y equals just x times y. Okay, but notice that if we started off on the other side of the equation, which is the property that we're trying to prove, the absolute value of x times the absolute value of y, well, since the x is less than 0, the definition would tell us that the absolute value of x equals negative x. And since y is less than 0, the definition tells us that the absolute value of y is negative y. Okay, and now you're going to have a negative times a negative. So those negative signs will cancel, and you'll just be left with x times y. But notice that's what we got up here. Okay, so that means this and this both equal x times y, so these two things must be equal to each other. So we can say that in case 2, the absolute value of x times y just equals the absolute value of x times the absolute value of y, and we've shown what we need to show for case 2. Okay, let's move on to case 3. And case 3 is basically that one of them is negative and one of them is positive. So without loss of generality, you could just pick one of them to be negative and one of them to be positive or 0. So I'm just going to say, I'm just going to pick x to be the one that's greater than or equal to 0. Okay, it wouldn't make a difference if I picked y to play that role instead. But I'm going to say x is greater than or equal to 0, and that y is strictly less than 0. Okay. All right. So what happens here is the following. What could we say about the absolute value of x times y? Well, notice that since 1 is positive or 0, which is x, and 1 is negative, we're going to have either 0 times a negative, which will be 0. Okay, then we'd be taking the absolute value of 0. Or we're going to have a positive number times a negative number, and we'll be left with something negative. And the definition tells us then that whatever's in the absolute value bars, if it's negative, you need to times it by a negative to make it positive. So our definition would tell us here that this is going to be x times y, but multiplied by negative 1 to guarantee that it's going to be positive. So notice that if x actually is 0, this is still going to be fine because you're going to have 0 inside the absolute value bars, and then on the right-hand side, you're going to have a negative sign in front of 0, which is just going to give you 0. So it's still going to work out if x happened to be 0. Okay, so that's what the definition would get us for the absolute value of x times y. Just write the definition here again in case it's hard to recall. So the absolute value of x is just going to equal x so long as x is greater than or equal to 0, and negative x if x happened to be negative. Excuse me. So what can we say about the absolute value of x times the absolute value of y? Well, we know x is greater than or equal to 0, so the definition tells us that we're in this case, and we should take the absolute value of x just to be x. Now, since we know that y is less than 0, okay, so that's what we assumed for case 2, we know that the definition tells us to just take the absolute value of y to be negative y. So we're just multiplying x by negative y, which we could just write as negative xy. Okay, but notice that That's what we got before. So if this and this just come down to negative xy, they must be the same thing. So we could say that the absolute value of x times y is equal to the absolute value of x times y. In this case, the absolute value of x times the absolute value of y. In this case, where x is greater than or equal to 0 and y is less than 0. Now, case 4, which isn't really another case 4 would just be saying that y is the one that's greater than or equal to 0, and x is the one that's strictly less than 0. Notice that that proof would unfold in exactly the same way as this proof unfolded. You just have to swap x and y around like this. So you just go through the case 3 proof, swap x and y around, and you would have the proof for case 4. So I guess it is, a fourth case, but it's just structurally identical to case 3. So I'm not going to go through that because you won't learn anything. Now, the last property that I want to mention in this video, this is the one that I won't prove. And this property says that for every pair of real numbers, let's give them a name, x and y, x and y. This is always the case. If you took the sum of x and y and then took the absolute value, whatever you get is always going to be less than or equal to what you would get if you just took the absolute value of x first and added it to the absolute value of y. Now this is called the triangle inequality. That's what this property is called. This is the triangle inequality. Triangle inequality. Now, I won't prove this one because the proof would, there's several ways you can prove it, but often it relies on other properties of absolute value, and then I'd have to go and prove those as well. So for example, another property of absolute value, so here's a bonus one, is that if, for instance, the absolute value of x is less than, let's say, some real number, less than or equal to some real number a, actually I'll state the property like this. So the absolute value of x, okay, that's always going to be less than or equal to x, but it's always, the absolute value of x is always going to be greater than or equal to negative x. Okay, well, this pretty much follows from the definition, but this property is often used to prove the triangle inequality, and the triangle inequality is basically indispensable in mathematical analysis or real analysis, any kind of analysis, which is the branch of mathematics that evolved from calculus. It's for proving theorems in calculus, proving that the objects of calculus make sense to talk about because they have some kind of existence. But yeah, this is the triangle inequality. I will talk about a geometric interpretation of it, or kind of what motivates it. It might not be clear in this video how this really connects to triangles, but let's say we have a triangle. Okay. The intuition here is that the shortest distance from point A to B is always going to be a straight line. So let's just imagine that this here is like point A, and this here is point B. What the triangle inequality ends up saying is that if we imagine that this side is X, and we imagine that this side of the triangle is Y, and we imagine that this side of the triangle is Z, well, the lengths, the combined length of X and Y is always going to be more than the length of Z. That's what the triangle inequality comes down to. Because notice that Z is just a straight line from point A to B. Okay, so Z just goes in a straight line from point A to B, whereas X and Y don't take a straight path. Okay, because, you know, this path from A to B goes straight and then changes direction. Okay, to get to B. All right, so that's always going to be the longer way of getting to B. So the triangle inequality basically says that for any triangle, okay, if you add the lengths of two of the sides, it's always going to be longer than the remaining side. Okay, anyways, more on the triangle inequality in the future in the mathematical analysis series or the real analysis series. What I'll do now is I'll talk through a geometric interpretation of the second property we proved. Okay, this one here. Okay, so remember that one said that if you just took the product of x and y and then took its absolute value, that's the same thing as if you just took the absolute value of x and took the absolute value of y and then took the product of whatever you got from both of them. Okay, so let's consider a geometric way of understanding that. See, proofs, they by definition prove a mathematical statement to be true, but what they don't always do is really show us intuitively why the statement is true. Okay, let's imagine a real number line. Do it in red. Seems to be my habit in the last few videos, doing a real number line in red. Again, remember that absolute value is just distance from zero. Okay, from zero. And I'll write the property again. Okay, so the absolute value of the product of x and y is just equal to the product of the absolute values of x and y. Okay, well, let's imagine that x is 3. Okay, so let's say x equals 3 and y equals 2. Okay, well, so let's say this would be x, and this would be, sorry, that would be y, and this here would be x, because x is equal to 3. Well, what would their product be? Okay, so 2 times 3, if I can count how many bars I drew, would be 6. So that's what x times y would be. So the absolute value of x times y, okay, in this case, where x is 3 and y is 2, this would really come down to 3 times 2, okay? Now let's suppose we resolve 3 times 2 inside the absolute value bars, and now we're asking what the distance of 6 from 0 is. Well, it's just 6 units. Okay, so this is like saying, look, if you've got two positive numbers, okay, and you multiply them together, what you're going to do is get a length from them or a distance from 0. Okay, and what that is the same as doing is just first finding out what the length of the first number is, that's x equal to 3, and then secondly finding out the length of what, or the distance from 0 of what the second number is, and then multiplying those two lengths or distances from 0 together. Okay, so you could first just multiply them together and then find out the distance from 0, or you could find out their distances from 0 first and then multiply them together, and you'd get the same length. Okay, and we'll just basically go through the same intuition, but in cases where they're both negative. So let's say that now x is equal to -3 and y is equal to -2. All right, and we'll draw another number line. So I'll stick with red for my number lines. Okay, so this is a real number line, and we'll put 0 here. Okay, -1, -2. So that's what y is equal to. And then we've got -3. Okay, and here would be 1, 2, positive numbers. So what would happen here is if we consider the absolute value of x times y, in this case, we would end up with -3 times -2. Okay, and this would just give us, I know this is algebraic at the moment, but this would just still give us 6. Okay, and what we would be doing here, and then we'd say, you know, the distance of 6 from 0 is just 6. But what we would be doing when we say this is saying, well, look, let's take the product of the two numbers first, and then find out what its distance from 0 is. So let's say we've got, this isn't drawn to scale, but here would be -6 all the way out here. Well, actually, we'd be talking about +6, which would be somewhere out here. Okay. Let's bring back my ruler and extend the number line. Okay, what we'd be saying is that, look, what you do is just multiply these two numbers together, right? And what you'd get is this out here. And then we'd ask how far we've gone from 0, and the answer would be 6 units. Okay. But now the left-hand side here, okay, so we just considered the case of the right-hand side. Now we're talking about the left-hand side of that property. This would be like saying, well, what you can, another way of doing it would be first to think about how far -3 is from 0. Okay, so that's like the absolute value of x, because x is -3 in this case. And then consider what the distance of -2 is from 0, which is the distance of y from 0, right? Figure out what their lengths are, and their distances from 0 would just be 3 and 2, so +3 and +2 respectively, okay? And then just multiply them together, and where would that take you? That would take you out here to 6. Okay, so it doesn't matter whether you just take their product first and then see how far away from 0 you end up, or see how far away from 0 each of them are individually and then take their product. Okay, and a pretty similar thing, it just happens for that third case where we say, okay, well, suppose one of them is greater than or equal to 0, and suppose that y isn't. It's less than 0. And then we draw a number line. Okay. And let's say we'll put 0 down here. Okay, and let's say that x is equal to, so x being greater than or equal to 0 is equal to 3, and y being less than 0, let's just pick -2 again. Okay, it wouldn't make a difference whether we just multiplied 3 and -2. So we took their product and saw where we ended up, which would be at -6, and then just asked, well, how far away is -6 from 0? And our answer would be that it's 6 units away from 0. Or whether what we did first was see how far away 3 is from 0, like this, and asked how far does this line extend away from 0, and then did the same thing with -2 and said, okay, how far does this line extend from 0? What's its distance from 0? Well, this one here is 3 units away from 0, and this one here, okay, that one is 2 units away from 0, and then took their product to end up at 6. Whichever order that we do things, we always end up saying that we're 6 units away from 0. So even though proofs are the more rigorous way of coming to terms with why something is true and showing it to be true, they don't always give you a good intuitive feel as to why something is true. When you look at things graphically or geometrically like this, it often gives you a much better intuition as to why things are true. So that pretty much wraps up my video on properties of absolute value. I hope it's helpful. Whenever you find yourself confused about an absolute value problem, just go back to basics and understand that what's being talked about is just distance from 0. I respond to comments, so if you have any questions about this video, feel free to post them in the comments and I'll get back to you when I can. Usually within 2 days. I try to make it within 1 day, but my schedule doesn't always permit. Like the video if you found it helpful. Feel free to share it with your friends and subscribe if you want to see more. Bye for now.